Good morning, everyone, and thank you for joining us on our latest webinar, Escalate with Aluminate-Optimizing LADH Performance. The heart of a direct lithium extraction process is the sorbent used in recovery of lithium from brine. Sorbents with base materials of aluminum, magnesium, or titanium are the most common sorbents used in the DLE applications today. However, simply selecting one of these sorbents does not guarantee good lithium recovery if the process used is not optimized for its operation. In our webinar series, we examine and discuss the use of lithium aluminate layered double hydroxide chloride, sorbents, contaminants of concern, and how to maximize lithium recovery by optimizing process operations. I would like to welcome Grant Thornley, who will be our speaker today. He is our VP of Engineering Solutions, and now we'll pass him the floor.
Great. Well, thank you very much for the introduction, Kayla. Most appreciated. And thank you for everyone that's joining us today for our webinar on lithium aluminum double hydroxide sorbents and performance, which is part of our DLE webinar series that can be found on our website. We're doing this webinar due to the requests made by people from the DLE discussion group and from emails that have been received. So without further ado, let's start the webinar off. Make sure that everyone can see. And Kayla, if you can just confirm that you can see my screen. Yep. Okay, excellent. Thank you. So, Escalate with Aluminates, optimizing lithium aluminum double hydroxide performance. There we are. So, just as a start, where is the lithium extraction within the DLE process? We've talked about this before in prior webinar. We have, if I take a look at block unit processes, kind of a block diagram. I have kind of a pre-DLE, which is any suspended solids removal, maybe some contaminant removal, maybe temperature, pH adjustment, and then into our lithium extraction. This is what we'll be talking about today, is using LADH as our media for lithium extraction. And of course, there's other webinars within the webinar series that talk about these other processes. So taking a look at, just as a recap from the market space, we know that there's different technologies used in the DLE process. There's absorbents, which is what we're talking about today, is lithium aluminates, or aluminum-based ion sieving, which is typically manganese or titanate-based. There's also solvent extractions, membrane separations, electrochemical, and other technologies on the horizons that are being developed. The most mature and probably the most dominant within our market space right now would be one, absorbents, which would be the aluminum-based, and two would be the ion sieving. I'm going to say more of the titanate-based. So those are kind of the two you see. Solvent extractions is around. One of the challenges with solvent extraction is that, hey, you get very good eluate quality. The problem is that you have organics in the depleted brine, which is being a bit of a difficulty with getting the permitting from them. But anyways, that's the subject matter for another day. So the type of exchange materials. One is just a differentiation of ion exchange. Ion exchange is typically used in post-DLE processes, referred to the unit process as polishing. Polishing, taking low concentration contaminants out of the eluate, such as calcium, magnesium, maybe sulfate, or boron. The sorbent material is used, brine is fed into the sorbent materials to extract lithium directly from it, and theoretically, no other ions should be absorbed into it. That's not the case, however, but theoretically, that's what the target is. Aluminum-based absorbents, a little bit different from the others because you use water to elute lithium off of the resin. So we flow the brine into the media, and then we use water to strip or elute the lithium off, which is a little bit different from a manganese-based or a titanium-based, which is an ion sieving material, not a sorbent. And I should point out that the aluminum-based, what you're actually absorbing lithium chloride onto the media, whereas the manganese or titanium-based you're exchanging or absorbing lithium onto the media, just as a good differentiation between the two operations. So different people manufacture and supply. I mean, there's lots and lots. This is just a slight example. So Summit, DuPont, Lanchin, Sunres, and Chemera for aluminum-based. Lilac, JMAG are magnesium-based. And as an example of titanium would be conductive or geolith. So as I said, good to understand the difference between a sieving and an absorption resin. Absorption is the lithium chloride comes onto the media. Ion sieving, it is the lithium. Usually it's being exchanged by hydrogen. It's the materials protonated, typically regenerated with a hydrochloric. So if you're using hydrogen as your proton, and that exchanges with lithium. But we're talking about absorptions today. So what does a lithium aluminum double hydroxide chloride intercalate sorbent look like? And forgive me for spending a little bit of time on this, but because I think it's really important for you to understand the physical structure of the sorbent material, the crystal structure of it, and how it's oriented, to really get a better understanding and appreciation of what happens in its operation and what happens when you have contaminants of concern enter into it. So I like to have a good visual. I'm a visual learner because this helps me out when I'm running through the processes and modeling and trying to do troubleshooting regarding optimization of the sorbents with clients. So the LADH is typically most used in media operations. I'm going to say around like 80% within the market. That's what I see. Manufactured, there's always talk about when you take a look at and you're selecting a DLE media provider, particularly for aluminum-based sorbents, it's about 3 to 8 milligrams per gram of media. Typically, what I see is 3 to 5 milligrams per gram. So I've yet to see 8 milligrams yet, but I'm hoping. Newer sorbent materials, because technology does evolve, what they're projecting is that they'll be able to achieve a 9.35% milligram per gram media. And so that's great. So people that are operating right now, maybe at a certain capacity, keep your eye on the horizon, because aluminum sorbent materials of higher capacity will be coming out. And when that happens, great to kind of pause, maybe redo your economic assessment of your plant using that higher media to see if it makes sense, if you should or should not be changing your media out at that time, in which to maybe get a higher lithium recovery via a higher volume in your lithium product production. So as I indicated, that lithium chloride absorbed into the inner layer material, or intercalation. Intercalation, just so you know, it just means that the lithium ions can come on and come off. So it's a reversible inclusion or insertion of a molecule into layered materials. That's the official definition or technical definition. So if you take a look at this, here's this. This is an aluminum layer right here. And then in between, you see this, this inner layer. What occurs, lithium comes onto, is absorbed into the aluminum layered, and then the chloride comes into the inner layer. So this is kind of a physical structure of it. And here's a kind of a planar view of the structure itself as well. So as I said, forgive me for belaboring this. So another slide on the structure. So more of a simplified graphic is, here's the lithium aluminum hydroxide layer, and there's, in this example, there's two of them, and this is what I mean by the inner layer. So it's the formal crystal structure is lithium. number of aluminum ions, it's a hydroxide, number of chlorides, and then water. And this is water in between. The integer of water within this space can vary, just as the ratio between lithium and aluminum can vary between manufacturer to manufacturer. Well, I think I've mentioned this later on in the presentation, but different media suppliers will use different formulations, dopants, binders, polymers within the manufacturing of that, which means, and also at different ratios. So even though you have a lithium aluminum double hydroxide sorbent, it doesn't mean just because you have that, it's going to perform the same as someone else's sorbent because of the differences in the formulations. And that's why we find within the DLE testing and the evaluation and selection of sorbents that you have to do physical testing because of the variations and differences within the formulations can have, this is crazy, even slight changes in the formulations can impart significant performance changes within the media, some good, some not so good. The inner layer molecule is charge balances. So when we said that we have lithium ions coming in, one of the important aspects of the inner layer is that as lithium ions come on, chloride ions come in. So lithium is a cation, chloride is an anion. Why is that important? Why am I stressing that? It's because you want to make sure that the structure is always charge balanced. So if I bring one lithium ion in, I want to bring in one cation, I want to bring an anion to basically neutralize those charges. So you always want to have a zero charge on the crystal structure. If there was a charge, then you could have charge repulsion, and that would impede the media performance. So it's really important that if I'm bringing one lithium ion on, I'm bringing a chloride ion to charge balance that structure. Zero charge you want on the sorbent. Here's another way of taking a look at the structure. As I said, it's important for you to kind of visually understand how this structure functions and operates, because it gives you better insight when you are doing your testing and evaluation and assessments. This may, by having that understanding, may allow you to deduce maybe what's happening in the media performance and how you might be able to optimize it. So right here, you take a look at is that the purple is the lithium ions. So there's just a couple here, and the amount of lithium ions here is actually dictated by the formulations, but lithium is within, this is the aluminum layer. Lithium is absorbed into the hydroxide layer, and then the chloride represented in green is what comes into the inner layer. So, sorry, another diagram, just in case you didn't get it, as I said, it's important to understand, is I like this as a little bit better a visual representation. This is the aluminum hydroxide layer. Remember, there's two layers in the inner layer. This is just a visualization of that upper layer. And what you see is that this is the lithium aluminum hydroxide, and you see that there's these octahedral voids within the structure. And this is important because this is where the lithium is absorbed into the structure. So those octahedral voids, not everywhere, you've got a couple, that's where the lithium comes in. Now, different sorbent medias will have different numbers of octal sites, or different numbers of, or how many moles of lithium can be absorbed into that, into a unit of that sorbent. So anywhere from 3 kind of like 3 voids to 4 voids to 5 voids, so to speak. Of course, the newer lithium is the kind of the 5 voids, or voids which aluminum can be absorbed into. So the other component is we know that what this structure is, and we also know through magnetic resonance and electron scanning, is that this is about a 0.6 angstrom, really, really, really small. This is on the atomic scale. This is a small void area. And why is that important? Well, because lithium selectivity works by partly, majority of size exclusion, meaning that you can't push a basketball through a pinhole. So if a ion is not the right size, if it's too big, bigger than 6 angstroms, it's not going to be able to be absorbed into that void. So lithium is the right size, so it's absorbed onto it. Now, when we talk about size exclusion, just for differentiation, this is what this chart is over here, that lithium as a neutral element has a certain radius. When you have a charge, a lithium ion +1, it actually has an ionic radii or radius, which is larger than the neutral. And this is what you're interested in, is that ion, what's the ionic radii? And is it smaller or bigger than 0.6? Because that's going to dictate what gets into the media. And remember, the only thing we want is lithium. We don't want anything else in the eluate, just pure lithium. That's not the case because some of the ions are about 0.6 or smaller. So that's just a very rough understanding of how selectivity works, is by size exclusion. So some of the typical selectivity performance of a sorbent, of an aluminum-based sorbent material is lithium, preferentially absorbed. Second is sodium, potassium, calcium, magnesium. Now, depending on the manufacturer of the sorbent, maybe this might change slightly because of the formulation, but typically lithium and sodium, those are going to be the preferred ions to be absorbed into the media first. So that's what we call our selectivity range. Go. Now, water content. Water content is also important within the media. One, it helps to facilitate the transport of the lithium and chloride ions in and out of the media, lithiation, delithiation. Within that, the water content within different daily medias will vary. The integer could be from anywhere from 1.5 to 4 on the amount of water or hydration, water molecules attached to that to the inner layer, which we refer to as hydration. The more water that you have, we found that the better the swing, meaning the easier that the lithium and chloride come in and out of the medium. So an important thing in operations, because the water is allowing that transport, it's really, really important that you never, never, never let the media dry out. And that means that when you're operating, that if it's in a resin vessel, that you always, the media is always below the surface of either brine or the eluate. It's always covered. It's never allowed to dry out, because if it does dry out, you're not going to recover that media. It's going to be very hard to rehydrate it, meaning get that water back into the crystal form. So take away from this, never let your media dry out, because the water is so important in the transport of lithium and chloride. So another way of looking at the sorbent is taking a look at the lithium aluminum or the aluminum hydroxide layers. What happens during the lithium absorption desorption process? So in lithium absorption, remember we talked about those octahedral voids? The lithium comes into the octahedral voids, and let me just quickly say that the lithium's not bonding to it, it's binding to it. It has weak van der Waals forces that are basically pulls and holds the lithium in place. So because it's not covalently bonded, it means that the lithium can easily come on and off, right? Very different from being covalently bonding, it's binding. So in A, lithium comes on, I fill that void. Remember we said that hey, I do not. So if the lithium comes on here, that means this structure has a positive charge. And if it has a positive charge, that means other positive lithium ions could be repulsed by it, because like repels like. So that's why it's important not to have a charge. So how do we do that? Well, the chloride comes into the inner layer. And this is the interesting part of the aluminate sorbents, is that the actual layers, the aluminum hydroxide layers, actually expand and make room for the chloride ions. So the layers, just so you know, are not chemically bonded to each other. They're actually held together by weak van der Waals forces, and we call that a weak van der Waals gap. As chloride comes in, the actual layers actually separate and accommodate the chloride to come into this space. So the process continues and continues. We load more and more lithium, and we see that we've got all the voids are filled. The chloride, great, it's charge balancing, so I have a zero charge on this structure. And then when I do desorption, the opposite happens. I use water, and it pulls the lithium and the chloride out, and you see that the structure just comes back. So we call delithiation. The structure comes back, and the whole process is started again. So just to let you know, that's how we do it, and that's why it's important to have the charge balance on this using the chloride, but also letting you know that the media, the layers do move a bit. It's not chemically bonded, and that's the uniqueness of the sorbents, unlike manganese or titanates, which wouldn't move. So understanding that lithium comes into the voids and chlorine comes into the voids. And we talked about size exclusion. Well, lo and behold, some ions are, 0.6 angstrom that can fit in those holes. And there's other contaminants that can chemically react or cause disruption within the LDH structure. And some of those common or potential contaminants of concern, because remember that every DLE media is manufactured different. Everyone has different formulations, and those formulations, the chemistries, binders, dopants use different ratios. So just because, again, you have an aluminum sorbent, it doesn't mean it's going to operate the same as everyone else's. There's differences. And vis-a-vis why that I call these contaminants of potential concern, because depending on the different formulations used, some of these contaminants may or may not impede, have negative or impede the performance of a media. So it's important, again, really understand what's in your brine. Good brine characterization. That's the first step in this entire process. Spend the money, spend the time, get a good characterization. Even if it's, a couple of ppm or whatever, it's good to know, because even at 1 ppm, a contaminant can cause or impede performance of medium. I've done it. I've seen it. That vis-a-vis why you need to perform physical testing of the media to see how it's going to perform. Mathematical modeling is really not going to tell you that. Only a back of a napkin estimate. Testing is going to tell you. So, contaminants of concern. Let's take a look at carbonates. So in carbonates, we're going to say bicarbonates. So I have HCO3, and I have an alkalinity curve. And at certain pH, I have alkalinity in my brine, which is very common. So the concern is that with the alkalinity, the bicarbonate, which is HCO3, can be converted into a carbonate. So hydrogen comes off. So it'd be CO3 2 negative. And that when the bicarbonate comes in here, this is theoretical, but there's I have some empirical data to show that this is actually happening. That the bicarbonate comes into this layer, and through the function that we have dissociation of the bicarbonate to carbonate. And with the carbonate, what I have that now it's sitting in the inner layer. And if there's any calcium in this, as an example, it can complex with the carbonates. So I have my carbonates in the inner layer, and I have calcium within my brine, and all of a sudden it complexes, and I have calcium carbonate solid forming in the inner layer. Now, remember we talked about the inner layer moving back and forth as through absorption or desorption or lithiation, delithiation. Well, if I have solids trapped in there, I'm not going to get any movement. In fact, I'm starting to plug. Think of these as channels. I'm going to start plugging those channels. So the ability for chlorides to move freely through the inner layers becomes inhibitive if I have solids. So calcium alkalinity can be a concern. Sometimes it can also be addressed if I adjust the pH. That if I have bicarbonates and I reduce the pH, I can actually convert the bicarbonates to CO2 or minimize the amount of bicarbonates in it. But this is just an example of showing you if I had some type of precipitate form in the inner layer, it's going to block the transport. And then what happens is that I can also start getting this charge imbalance, right? Now I can't get enough chlorides in here to charge balance the lithium via the structure takes on an ionic charge, and I can have charge repulsion of the lithium, which means that I would have negative performance or an impedance of lithium absorption. So that's just one. The operating of a lithium sorbent. One of the key things, because it's aluminum based, one of the key operation pH is really dictated by the solubility of the aluminum. So if you take a look at a chart over here at the left, you can kind of see that the aluminum, around 6 pH, that's where I'm getting this minimum dissolution of the aluminum. And aluminum will dissolve at a low pH, aluminum will dissolve at a high pH. So we're just trying to find this optimum point. And that optimum point is around 5.5 to 6.5. So when you're operating an aluminum-based sorbent, you typically want to target a pH of about 5.5 to 6.5 because you want to minimize the amount of aluminum that can be dissolved at low pH or high pH. So that's a rule of thumb. That's the pH you're operating. Titanates or magnesium, very different. But for sorbents, 5.5, 6.5. And when you do your testing, that's going to allow you to figure out what the optimum pH is. Temperature, when I'm operating a DLE media, well, quite simply, is if I increase my temperature, I'm going to increase the kinetics, meaning the movement of the molecules back and forth. Think of it, if it's really, really cold, molecules don't really move that fast. And in fact, if I'm at 0 Kelvin, molecules don't move at all. They're frozen. Now, that's an extreme example. So as I heat up, the molecules move back and forth, which means there's faster and more rapid and more frequent bumping in contact with the lithium to the medium. So as I increase temp, I increase my kinetics and I get better performance. Typically, what you see from the DLE media manufacturers is a operating temperature between 10 to 60 degrees C. 30 degrees C is typically where I see. That's kind of where, around 30 degrees C is where I see it, or 40 degrees. Again, depending on what the DLE media you're using, what the operation is. Whatever you're looking at and doing your assessment, again, looking at, okay, if I increase temperature, quite easy, can increase the kinetics and get a better performance. That's always offset by the analysis of the economics versus the performance improvement. Meaning, if I have to heat it up, I got to put energy into it. So therefore, if I'm putting energy into it, I've got to see a better or a good return on my investment, or a higher lithium production or better absorption process in order to offset that energy increase. And through testing and working with your DLE media provider, you should be able to determine that. And lastly, LADH is elution water. So when I'm eluting lithium off of the media, I use water. So environmentally friendly, sounds great. However, what's been found in where I found through multiple tests and evaluations is that if you only use water, I mean a high purity water, low TDS, if you just use water, what I find is that you start stripping off lithium out of the physical lithium aluminum hydroxide layer. So remember, lithium is chemically part of the layered structure, right? So the voids go into the within the voids, lithium goes in there. However, that lithium structure, that layer, is chemically requires to have lithium in that crystal structure. It's part of the crystal structure. So when you use water, it actually grabs and extracts lithium from that crystal structure and it destabilizes it. So it can collapse the crystal structure over time. So, and what I've seen, I mean, it's easily seen when you're doing your testing, do a mass balance. And if you're finding that, okay, my brine is, let's say 100 ppm, and when I finish my recovery, I'm getting, let's say 110% recovery, or 110 ppm coming out the back end. Well, it's a mass balance. You're not gaining lithium from the brine. That lithium mass has to be coming from somewhere, and it's coming from the structure itself. So I mean, that's a pretty easy example of saying, well, if I'm at 110% lithium recovery, then okay, yeah, that's easy enough. I'm pulling lithium from the crystal structure. However, when you're running, and let's say the DLE media testing, that third party, the DLE media provider comes back and go, oh, I've got 90% lithium recovery. You want to see the mass balance because you want to make sure that that 90% recovery isn't because, partly because you're pulling lithium out of the lithium structure. And I'm telling you that if you're only using water on your eluent, there's a very high probability you're pulling lithium out of the crystal structure. So where am I going with this? If I was to then use water for my eluent, great, my stripping agent, perfect, low TDS, excellent. And I add in lithium at around 75 to 150 ppm into that eluent water, what happens is that because I have lithium in there, it actually stabilizes the structure. So it doesn't become hungry to pull the lithium out of the water because now I've got lithium in the resin, I've got lithium in my eluent water. So it actually stabilizes the structure. And that means I'm not going to be pulling lithium out of the structure. I'm going to be pulling lithium out of the voids. And that's what I want. I want to pull lithium out of the voids, not out of the crystal structure. And by simply adding 75 to 150 ppm into that eluent water, it prevents lithium from being pulled out. What does that mean? It means that it stabilizes the structure and it improves long-term operational performance. Again, worst case scenario, I pull everything out, the crystal structure collapses. I put lithium in the eluent water, it stabilizes the structure, and now I have good long-term operational stability, meaning that it's going to be a while, a couple of years before I have to change that media out, hopefully. So the amount of lithium you want to put in the eluent water is determined through your DLE testing and evaluation. But as a rule of thumb, 75 to 150 ppm of elution water. And as simple as this sounds, there's some DLE aluminum sorbent suppliers that will tell, oh no, we just run water through it and that's it. And I'm telling you, the probability, if they're just doing that, you're destabilizing the structure. So now you know. So what are, excuse me, what are the DLE media processing cycles? Well, there's three. And this is common with all the aluminum sorbent materials. There's absorption, lithium loading. That means we run brine through the media. Lithium is extracted and loaded onto the media. There's washing, which is an intermediate step between the absorption and desorption. And the washing step displaces brine from the media. And the last one is desorption, which is unloading of the lithium from the media. In each one of these cycle processes has unique operations and operating requirements. So the first one, absorption process. Well, brine flows into the media, and you see on the right here, I've just done a very rough diagram. Well, here's my resin vessel, also sometimes referred to as a contactor, that the brine flows in from the top. It flows through a plug flow, a very hydraulically, it's an even laminar plug flow that passes through the media and then out through the bottom laterals. That's how brine, wash water, and eluate is flowed through a within the contactor or DLE vessel in a downflow pattern. So the brine flows in a downflow pattern through the media bed, and the lithium is extracted. Sometimes what you'll see is on the brine that you may have to do a pH adjustment. If the brine pH is too low, remember we said 5.5, 6.5 for your operation. If it's too low or too high, I want to do a pH adjustment to get into that optimum range. Again, validated through my testing. Next, if I do a pH adjustment, sometimes I may precipitate solids out of the brine, depending on what the characterization is. So let's say I've got calcium and I'm bumping it up, and I used sodium hydroxide. Well, I may have magnesium hydroxide or something drop out, or calcium carbonate drop out. So this is why it's important to have a filter downstream or after your pH adjustment. So this is going to, I jokingly refer to, take out the sticks and frogs and body parts. This media, it depends on what the size distribution is of the particles in this. So just as a side note, when you do your brine characterization, one of the things you want to take a look at is the particle size and the size distribution. What's the biggest particle, what's the smallest particle, and what's the nominal particle? Because that information is going to dictate the type of filtration system you need, meaning that, do I need just a multimedia depth filter? I would take about 50 microns. Do I need a microfilter or an ultrafilter? Just so you know, the tighter the pore or the tighter the filtration, the higher the operating cost, because the differential pressure or the pressure required to drive that through changes. So that's why you want to do a size distribution, because if I only have to use a multimedia filter, well, that's going to be less expensive to operate than an ultra filter. All depends on what you're trying to achieve. The last thing is that you want to have filtration, because you do not want to be using your media as a filter. I mean, if I got solids coming into this is going to deplete the performance of this rapidly. So sorry to belabor that. So next, we're in our washing process cycle, which is an intermediate step between absorption and desorption. Why do we do that? It's a transition period or a transition phase process between the absorption and desorption, because during absorption, remember, we're passing raw brine through the media into the vessel, and the vessel has a freeboard, a space, and there's voids in between, or spaces in between my media. Well, when I stop the absorption process, right, I want to get ready for my desorption, well, I still have raw brine, right, residual within that tank. So I've got to get that out of the tank, or so the resin vessel or the contactor, before I start my absorption process. Because if I start my absorption process and I have raw brine, all the contaminants, and there's a lot of contaminants in the raw brine, is going into the eluate. And what's our objective? We want to have the cleanest and purest eluate possible. So by going through a wash cycle, we're going to purge and displace all that raw brine out there, which will allow me to have better eluate quality. And the way we do that is, again, a downflow process. And it's going to take out, here's that free space, or the head space above the resin. That's filled with brine. There's some brine down here. There's brine in between the resin particles. And I take water in a very laminar downflow, plug flow method. I push or squeeze the raw brine out of this. Now, I want to minimize the amount of wash water I use because we know that water is used to elute or remove lithium off of the media. So if I'm using water in this process, I want to minimize the amount of water used. Remember, the only thing we want to do is push the brine out. I'm not washing the resin. I just want to push and displace the brine out. So we only want to use about 1 bed volume, which is the media volume, 1 bed volume or 1.5 bed volumes. If you're using 2 bed volumes, I work with the DLE media provider and see if there's something you can do. If you're getting to, the more you wash your resin, the more lithium you're going to be absorbing from it. So you're going to have lithium loss. We want to minimize that by minimizing the wash volume going through it. The other, aspect of washing is that, remember we talked about temperature increases the kinetics. Well, if I decrease the temperature in my wash water, that will actually help me minimize lithium loss during that process cycle. So if that is an option, that you can decrease the temperature of your wash water, that will help in minimizing lithium loss. And again, we want to maximize lithium recovery and minimize lithium loss. And that is the wash cycle. Now, off to the right here, when you're doing your testing and evaluation and you're taking grab samples as you're eluting through, doing your wash and elution, what you find here is prior to the transition stage from wash to desorption, you can see that we're measuring, this shows that we're measuring the ions coming out the bottom of the resin vessel. And as we get to the end, as we push all the water through it and to the bottom of it, you'll start seeing that all these, the sodium, potassium, calciums, all these are decreasing because we're pushing it out of the brine and out of the resin. And then when we start, you can see that all the concentrations, which are really high, let's say sodium is really high, now sodium's really low. That's the key, just on a graphical representation to it, the importance of it. Now, to your last process cycle, desorption. So in desorption, lithium is removed or stripped from the DLE media using water. And we talked about that when you use water, we want to stabilize the aluminate structure, so we put lithium into that, and it's 75 to 150 ppm. Now, just like we said in washing, if I decrease the temperature, I reduce my kinetics and I will basically lose lithium. The other component is that if on desorption, if I heat it up again, increase my temperature, I can increase my recovery rate, and I can also reduce that process cycle time. So if that's available, then to add in energy, and again, if I'm going to increase the temperature, it means added energy, I've got to see return on my investment over here. It's that better performance, higher recovery lithium, and so on, because it's about economics. So that is an important aspect of it. Typically in the process cycle on sorbents, as I said, 30 to 40. Magnesium titanates, typically you're at much higher temperatures. And we'll talk about in the next DLE webinar about that. So in summing this up, when I'm taking a look at my sorbent, a couple of key specifications that I want to measure, and or if the DLE media provider is doing your testing, your beaker test or your fixed column test or maybe carousel testing, this is what I want to be reported on. I want to know what my absorption capacity is, how much lithium is being absorbed into the media. I want to know the selectivity, right? I've got lithium, sodium, what other? What's the selectivity range of this? My separation efficiency, my percent recovery, how much lithium I've got my absorption, but how much am I going to recover on the back end? cyclic stability is and thermal stability is the physical structure of the resin. Am I seeing it degrading quickly, or am I going to get good life expectancy out of this, like a couple of years before I have to change my resin out? Eluate purity, key. Can't stress that enough. When you're doing your testing, you want to grab a lot of samples of the eluate quality coming off. Typically, when you're doing your initial testing, like every bed volume, you don't have to analyze every single sample you grab, but it's good to have that if you need to go back later, you can take a look at that grab sample. So eluate purity, we really want to focus in on that. Extraction time, just basically how much time is my cycles going to take. Operating pH, and of course, at the end, really dictates the economics or economic viability of your process is your energy consumption. So, and that said, I hope you didn't fall asleep. Thank you very much for joining us in this webinar series. This was the Aluminates and how to optimize them. The next daily webinar within our series will be on titanates, and the one after that will be on manganese-based absorbents. So thank you again. Of course, any questions, please feel free to call me. I'm available the majority of the time. And if you're interested in our webinars, go to our website at www.forwardwatertechnologies.com. Take a look at our webinars, and we have lots of webinars on different technologies and processes of DLE. And lastly, if you're interested, you can also join the DLE discussion group on LinkedIn. So in that, thank you very much, and I look forward to talking to you in our next webinar. Take care.